Morning, I'm here to talk to you about something that you absolutely do not need to know to do well on your AP Chemistry exam. So, why am I even making this video? Because for Chapter 12, Chemical Kinetics, you are going to be using rate laws, differential rate laws and integrated rate laws. And both of these rate laws have a constant inside, little k, known as the rate constant. Now, I refer to this as little k because for equilibrium we have big K. So I'm going to keep on saying little k, little k, little k, or I could say rate constant, but they mean the same thing. So your rate laws have rate constants inside. This is an example of a rate law for a first order reaction, okay? Something to keep in mind is that the magnitude of K, the magnitude of our rate could be very, very small or very, very large. So just keep that in mind, okay? There's no real limit on how fast or how slow a reaction goes, okay? So that being said, this video is about explaining where does little k come from. And the answer is little k is unique for every single reaction under every single set of reaction conditions. So if you change the temperature, you are going to change the value of little k. If you change the particles that are reacting, the chemical reaction, then little k is going to be different as well. So I'm going to explain to you how that can happen using the Arrhenius equation. So the Arrhenius equation is K equals A times e to the power of minus EA divided by RT. You should know what all of these things are apart from A. So I'm going to explain to you first what is A. A is unique to every kind of chemical reaction and is a factor of how often correct collisions occur in a chemical reaction. I say correct orientation. What I mean is that the right parts of each reactant are colliding with the right parts of the other reactant. So, and this can clearly be different for different reactions. So for example, if we look at this top reaction here, we're looking at two atoms colliding to form a diatomic molecule. It seems very much to me, and I hope you agree, that these are whizzing around maybe inside of our container. It doesn't matter if they're rotating, it doesn't matter what orientation they hit each other at, it should be possible for them to form a chemical bond, no matter what orientation they collide with. So it's fair to say that these collisions are more or less always going to be the correct orientation. So would we expect the rate of reaction for this reaction to be slow or fast? We might expect it to be fast, based on this information alone. Then we can compare it to another reaction. How about we have this long chain of circle particles colliding with this square, and the square can only attach to this third circle. As you can see, there's going to be a much higher frequency of inefficient or incorrect collisions, which don't lead to a chemical reaction occurring. So if someone were to ask you, these things under the same temperatures and conditions, etc., which one would you expect to have a faster rate of reaction? You could say this one, because you expect that the number of correct orientation collisions to be greater than for this one. I hope that makes sense. So A is unique for every reaction and is a factor of how often correct orientation collisions occur. So now that we've cleaned that up, let's have a look at e to the power of minus EA divided by RT. So the first thing to ask yourself is, if the rate of reaction is going to be fast, do you expect the activation enthalpy of this reaction to be high or low? Low. I hope that you realize that. Because the lower your activation enthalpy, the easier it is for particles to overcome that bump in our enthalpy graph, yeah? How about the temperature? So would you expect the rate of reaction for something to be higher or lower at high temperature? So high temperature equals what kind of rate of reaction? High rate, fast rate, exactly, okay? And this is something that can be quantified using the Arrhenius equation. So the first thing to note is this minus number. The Arrhenius equation uses e to the power of minus EA divided by RT. Now this is the same as, if we go down here, the same as 1 over e to the power of EA divided by RT. So basically, we want this number down here below the 1 to be as small as possible so that overall this number is large. And if this number is large, then our K will be large, and therefore our rate of reaction over here will be very large as well, okay? So it all connects together. So we go back over here, you understand that if you plug a small number into EA, it is likely that this part here is going to be small, therefore our K is going to be large. Alternatively, if we make our T very large, then this part here is going to be small, and therefore this is going to be larger, and K is going to be larger, okay? So this is how temperature and activation enthalpy affect the rate of a reaction, which I think is quite common sense, but it's just nice to show you the Arrhenius equation to give you a more basic understanding of where this little k comes from. So remember, little k is different for every chemical reaction, or will be different at different temperatures.